In this video we are going to discuss Lenz's law. In last video we discussed about Faraday's law and we got one mathematical expression also. So in Lenz's law he modified that mathematical expression of Faraday's law in this way. Let us see that. Okay, the statement is that the polarity of induced EMF in a closed circuit or coil is such that it opposes the cause which produces it. Opposes. What opposes? This induced EMF. This E, it opposes the cause of induction. The cause of induction is which one? D phi dt is the cause of induction. Means the change of flux. Because in all the three experiments of Faraday, what we saw? That in every case there was a change of flux. And when there was a change of flux, there is a formation of induced EMF. Okay. So it opposes. That is why there is a negative sign. And this capital N means it is the number of turns. Suppose if one coil is having this, suppose 3 number of turns, then this N will be 3. Okay. Anyways, this mainly our focus is in this negative sign. That's what Lenz gave in his law. The polarity of induced EMF. It is opposite. Okay, or it opposes the cause of induction. So that is why E equals to minus N d phi dt. Alright. Now Lenz's law, it is in accordance with the law of conservation of energy. That means somehow using Lenz's law we can get the concept of conservation of energy. Means it is Lenz's law is following conservation of energy. How? Let us see that. Very important part, this one. Suppose conservation of energy means what? Energy cannot be created or destroyed. It just gets converted from one form to another. So here, when there is a magnet, suppose this is a magnet, this is a coil, right? When the magnet is in motion, this side or that side, the coil, in the coil we get current. So current is a form of energy. So since we are getting current here, this current has to be converted from some other forms of energy. Suddenly how current can produce in a coil? So that is well explained by Lenz. What he said, when there is a coil like this, very important thing, okay, try to understand what I am saying here. There is a galvanometer, it detects the current, and then there is the coil. Suppose the coil is brought towards the magnet is brought towards the coil. Which pole of magnet is brought towards the coil? North pole. Then when it is brought towards the coil, it is seen that in the coil there will be formation of induced current. The galvanometer is showing deflection. And we know that when in a coil there is an induced current, it's like solenoid, right? One pole of the solenoid becomes north pole, one side becomes south pole. It is seen that this side becomes north pole and this side becomes south pole. Means when north pole is approaching towards the coil, this pole of this solenoid behaves like north, this pole of the solenoid behaves like south. As a result, what happens? As a result, what happens is this north is brought towards this and there is again formation of a north pole. That means between these two north poles there will be repulsion. So in other words, the coil is repelling the magnet to come near it. Okay. As a result, when we are bringing this magnet towards the coil, we have to do some amount of work against the repulsive force, because there is a repulsive force. This coil, it is not allowing this magnet to come near it. So if you want to bring this magnet towards the coil, you have to do some work, and that is the mechanical work which is being converted to current in the circuit. In the induced circuit we are getting, in induced current we are getting in the circuit. So if we are getting induced current, since it is electrical energy, some amount of energy should be converted in electrical form. What energy is here which is converting? mechanical energy, because we are doing some work is done means that is mechanical energy. We are providing some mechanical energy in the whole system, and that mechanical energy in turns it get converted to electrical energy. Okay, now what happened is, when this magnet is taken away from the coil, then how this mechanical energy getting converted to electrical energy? Then the reverse thing happens. Now what happened is, when the north pole is taken away from the coil, this side of the coil becomes south pole. That means the current in the circuit reverses. If in this case, if the current was, suppose if it is flowing like this side, then in the next case current will reverse, and if current reverses, their polarity will also reverse. Here it was north pole, here it is south pole. So if it is south pole, now it is going away, this south pole will attract this north pole and it will not let it go away. That means to make it, or to keep, or to take this away from the coil, again we are doing some amount of work done against this attractive force, because now there is attraction. This south pole is pulling this north pole towards itself and it is not letting it go. So if it wants to go, again it has to do some amount of work, mechanical work, and that work will be converted to current in the circuit. Okay, so in simple word, Lenz, what he said that it opposes the cause of induction. See, it is opposing. When it is coming near the coil, it is not letting it come. When it is going away from the coil, it is not letting it go. So that means it is opposing the motion. It is opposing the motion, and motion means, motion is the main cause of induction. When there is a motion, then only induction takes place. Or motion is the main cause of induction, or diffidity is the main cause of induction. And thus induced EMF is such that it opposes this negative sign. It opposes the main cause of induction. Followed? So in this way, Lenz's law, it also satisfies the conservation of energy, because the work that we are doing to bring the magnet or to take the magnet, that work is getting converted to energy. So that's what is written here. According to Lenz's law, the direction of induced EMF and hence induced current is such that it opposes the cause or motion of the magnet which produces it. To oppose the cause of motion, the upper face of the coil acquires north polarity, talking about this one. The north pole of the magnet and the north pole of coil repel each other. To move the magnet towards the coil, mechanical work has to be done to overcome the force of repulsion between the north pole and the bar magnet and the coil. Okay, this mechanical work done is converted to electrical energy, indicating the deflection in the galvanometer. So there is the law of conservation of energy. So Lenz's law is in accordance with the conservation of energy. Okay, similarly this is also mentioned. When it is taken away, this gets south polarity, so there will be attraction. Okay, so I think this part is clear. Then in this part, or in this chapter generally, the current that we are discussing, it is induced current, means it is not directly coming from a battery, but it is generating due to change in flux, change in phi or flux. Okay, so for induced current, the rule that we use, that is Fleming's right hand rule. In the previous chapter we discussed Fleming's left hand rule, right? This forefinger, this one index represents magnetic field, this one represents current, this one represents a force or motion. Okay, but in this case this is right hand rule, not left hand. The function of these fingers, that means the meaning of these fingers, that will remain same, only we are using right hand. For induced current, remember we are using right hand rule. Okay, index magnetic field, this one induced EMF, induced EMF, okay, or current. And this one is motion or force, you can say, because the direction of force and direction of motion is almost in most of the cases same only, right? So this rule we will use in this chapter. Thank you.